Um, Questions from homework? No question? Okay, that may be a good sign. That means you guys are okay, or that means you haven't started yet. If you haven't, you better start because we have a lot of homework stacked for this week. Oh, Aaron?
Can you go over implicit definition example again?
It's like the idea, not some examples, right?
An example of it would be great.
Example? Okay,
Yeah.
let's try that. How much have we done before? Let's see. Okay, for implicit, basically what we have is an equation involving x and y, and the y is not explicitly given. So you can have something like this. Okay, your job is try to find y prime. Do you guys want to do it yourself, Aaron, or do you want me to walk it through first?
I can do it myself first.
Let's try that then. Let's take 5 minutes, see how far you can get. All right. I would say your exam question gets no harder than this. Make it harder doesn't make it more complicated, but I mean, the ideas are the same. The rest is just how careful you are. When I grade it, I will focus on two things. Number one, did you do the derivative correct, which is up to this step? Second, do you understand that you need to solve for y prime, which means FOIL everything out, put all the y prime term on one side, everything else on the other side, and divide. Okay, it looks like a lot from here to here, but really you're just copying. Okay, so the majority part is actually how to take the derivative here, which is just the first two steps. Chain rule, product rule, okay, chain rule, summation rules. Okay, the rest is just, do you understand when you have a y there instead of x, you need to actually times a y prime every time you take a derivative of it. If it's x, fine. Is everything clear on this example, Anton?
Yeah, so I had one question. Like on the second step, when you, or actually, sorry, the third step, when you go from
Hold on.
y
Just let me
squared
use-
times cosine x
Here?
prime, why is there a y squared by the negative sine x?
Here.
Yes.
Ooh, let me take it out. Basically, what you're trying to do is you're trying to do y squared times cosine x prime, right?
Yeah.
Do you agree this is a multiplication, which we should apply the product rule?
Yes.
So it's going to be y squared
Oh,
prime
yeah.
plus y squared cosine x prime. That's where the y squared come from. You have two terms.
Got it. Makes sense.
Yeah. Adam?
Yeah, so why is that where, like right after that y prime, why is it minus secant squared?
Oh, yeah, kind of skipped steps. Technically, there is a negative sign here. So this should be a negative if I want to put it to be a positive, right? Do you see what I'm saying?
Yeah, that makes sense.
Okay, so
Thanks.
that's where the negative sign come from. Yeah. I kind of skipped the steps because I really don't want to rewrite this line, just change a sign. Okay, so you can do the same thing, but just keep in mind, every time you do that, you can see sometimes people lost it, right? That's why I say showing the steps, no matter how simple it is going to help other people to understand your work, which is very important. Do you guys know the story about Fermat's theorem? Conjecture, actually? Have you guys heard about this before? Either way, it's just a mathematical statement. Fermat is not a mathematician. He was a lawyer. He just does mathematics for fun. So what he does is he go into the library at night after he finished his whole day's work. He wrote down a theorem and he said, I prove it. He basically write this thing right next on the side of the book. And he said, but the space is too small, so I can't write the proof down. Okay, he said, I proved it, but I just didn't write the proof down. And then after that, people spent 300 years in order to prove this thing. So up to today, people basically say, okay, since you didn't write it down, we're going to guess you didn't prove it. Okay, it's probably the ultimate example of skipping steps. Basically, makes people think you are a fraud. So better show the steps. Otherwise, people can actually, get confused for 300 years just to figure out what you did. Okay, especially if you think your work is so valuable that even after you die, some people look at your notes. Okay, they will discover you're a great guy. Okay, you're a big mathematician. You better show all your steps. Okay. Yeah, I don't know if it's appropriate to say, but just write your steps as if you would die after this. So people will pick up your legacy and work from there. Okay, that's probably the ultimate way of thinking about how to write your steps now. All right. Everything good with this example? Okay, it's the old rule again, chain rule, product, quotient, whatever, combined with you're taking the derivative of y with respect to x. So when you do that, finish and times y prime. Okay. The second thing, the second thing we were talking about is trying to use this. We can find log and trig inverse. Okay, the first one is log. We did it last time. We said this is 1 over x. And this is 1 over x ln a. The way we did it is, if this is going to be that, then x equals e to the y. I don't know the derivative of this. I do know the derivative of this. Okay, but I need to use the implicit differentiation, which is times the y prime when I finish. In this way, I solved y prime equals 1 over e to the y. Therefore, it's 1 over x. That's what we did last time. Okay. Now, similarly, we can do this for all the trigonometry function now. What's the derivative of sine inverse? Well, that's just y prime for y equals this. But wait a second, this is the same as x equal to sine y. I don't know sine inverse. I do know sine y. That is going to be 1 equals cosine y times y prime. This implies y prime equals 1 over cosine y. From here, you can see if you know the inverse function, it's very easy to get it from the derivative of the original function. Getting sine inverse from sine, getting cosine inverse from cosine. Just do this nice transformation. Okay. After that, when you take the derivative, just use the derivative you know for the inverse function. You're all set. The rest is try to change this one to make it look nice. So technically, I want this one to be in terms of x. And I know x is in terms of sine y. So to get cosine y, I should take the square root 1 minus sine y square, which is the trigonometry identity with a plus minus. And eventually we will figure out this is going to be plus. So that's how we got sine inverse. It's your notes. Okay, that is up to now. We still have 5 more. And what I will do is I will quickly do tangent and secant, and then we will guess what is cotangent and cosecant and cosine. All right, so tangent inverse. This implies x equals tangent y. Okay. Because of that, take the derivative. Y equals secant square y, coming from tangent, times y prime. That's step 1. Okay, step 2, I don't like this. I want x. Knowing that x is tangent, then the question becomes, can you compute secant from tangent? And the answer is yes, by a trig identity. This is the trig identity. But once you have that, so we use the trig identity. Is the logic here clear? Okay. Knowing everything about tangent, you will be able to do this. And once you figure it out using different implicit differentiation, you can find tangent inverse. Okay. The detail you can check back later by rewatching the notes. It's really not important here. Just very, very quickly. Okay. Same logic. Secant inverse becomes secant, and you switch x and y. Derivative of secant, which is secant tangent, with a y prime when you finish. Again, you want to change it to be x. No, of course, this is already x. Now you want to change tangent to be in terms of secant. Before, we know how to change secant to be in terms of tangent by this trig identity. Then we just do the reverse. Let me make sure I'm correct. Which is x squared minus 1, which comes from secant. Take the square root with a plus minus. We will skip the detail, but it also comes from the domain requirement. But eventually, this will be the formula. Okay. You can check the details later yourself. The idea, however, should be straightforward. Eric, do you have a question or? Okay, yeah, just raise your hand if you have questions. Then, that's what we have computed so far. In the exam, I may require you to show how to find these two. Secant inverse is so rare, so we don't care too much about it. Of course, we still have something else. Now, if you know everything on the left column, can you guess what's on the right column? This is for cosine inverse. This is for cosecant. And this is for cosecant. It's basically exactly the same thing with a negative sign. All right. Any questions so far? If no question, every single formula we need for derivatives are done. Okay, up to now, power, we know how to handle it. Rational. Okay, quotient rule. Exponential, we know. Trig, we know. Okay. Square root, we know. Log, and the trig inverse. The whole thing is complete. We know every single thing I wrote here, which are called simple function. Everything here is done. Plus, we have 5 different rules. F plus G, F minus G, F times G, F divided by G, and finally F circle G, which come from the chain rule. So all the differentiation rules are done together. If you want, after this class, you should really create a table. That's almost like your formula sheet. Okay, and then memorize it. That table is basically the first half of calculus 1, okay? Derivatives. For the second half, you will do integral, which is the reverse table, knowing the derivative, how to get the original function. So I would say this table is almost like half the content of calculus 1. Sounds good? Every single thing here, we found it by ourselves. We didn't use any other help except for this one. Okay, remember we use a fact, which is e to the h minus 1 over h limit h goes to 0 is 1. This is something we took for granted because people have done that for us. Everything else, we get it from ourselves. Okay, so it's almost like we walk you through of a piece of human wisdom. Okay, this is some treasure passed away from our ancestors 400 years ago. We went through the whole process. Okay, so here it is, a piece of human wisdom, a huge piece of human wisdom. Okay, we should show some respect for what we just did. Anton.
Would you recommend that we refamiliarize ourselves with all the trig IDs for the tests?
The answer is yes, and nobody listened to me. So I feel like I should say yes, yeah. Okay. And you better do it. Because no matter what major you're in, since you're taking calculus 1, not business calculus, that means you're going to see trigonometry somewhere. Okay, and in calculus 2, you have several huge sections just on trigonometry. So you either do it now or later. I would say do it now, otherwise you'll forget. There's not much. So I would say sine square plus cosine square equals 1, tangent square plus 1 equals secant square, that's certainly 1. And how to say, tangent equals sine over cosine, that's certainly some other type. Other than that, you probably don't need to know sine A plus B because it's less often and you can look it up. And also like the product to sum and sum to product, that's something you have seen before, which is something you hate. Good news is the professor also hates it. So you probably won't see them. All right. That's it. Implicit differentiation is done. Now we want to go to the next one. Derivative of log. Okay. Number one, if it's just the derivative, there's nothing to talk about. We already know the formula. We did it ourselves using implicit differentiation. Okay. What we're interested in is actually the application of this. Let's see an example. Well, how to do this? Of course, we know how to do this. Quotient rule. Do you want to do it? You can see how hard it is, right? F prime G minus FG prime, and each F and G is itself is a product, and you square the bottom, and you have to simplify. It's a disaster. Okay, so quotient rule will work. We just don't want to do it. Product rule is better. Still, we hate it. Make sense so far? How much do we wish we don't have product, instead we have sum? How great it will be if you can change dividing to minus. Because then quotient rule and product rule becomes plus or minus, and plus and minus are easy. Sounds good? Does it ring a bell? You can change product to summation, and you can change dividing to be minus. Have you seen something like that before? That is what log can do. Try to recall. We do have nice properties. Well, let's take log. See what I mean by that. If y equals that, of course ln y equals ln that. That's all right. Second, now, if I apply ln on this thing, by the property of log, if you see a multiplication, you take a summation. If you see a dividing, you take a minus. Second property, if you see a power, bring it down. So the whole ln y become this after you split all the multiplications using the property of logs. Which again, they all the way back to pre-calculus and college algebra. Sounds good? Now you want to take y prime. You say, wait a second, I really don't want to take y prime of this. Then we say, since they are the same, how about we take y prime of this? Does it look nicer? Well, let's take a look. What's the derivative of ln? 2x squared plus 1. That's going to be chain rule. That's for ln, 1 over x, right? Times the derivative of the inside, so chain rule. The 1/3 is just 1/3. I want to focus on the second part. What's the derivative of ln? 3x minus 2. That's going to be 1 over x times this. Okay. Similarly, just keep going. And here I use nothing but the derivative of ln x is 1 over x and the chain rule. Just use these two things, I can derive all the derivatives. Now if I clean a little bit, not hard. -4 is just give me 0, so nothing to worry about. Did we do the product rule? Did we do the whole mass of quotient rule? Nothing. We just did plus minus, plus minus. And then every time we see ln, it's 1 over x times the derivative of the inside. Just use chain rule for multiple times. No product, no quotient, no mass. All right? Aaron.
Shouldn't that last 3x be 3 halves because of the 1/2 x?
Yes, I put it here.
Oh, okay. Okay.
No. And if you write it to be 3/2 times that thing, that's totally fine.
Okay.
Yeah, we're okay with either. Do you see the do you see the advantage of doing log, product rule, quotient rule? Not anymore. Okay, instead you have ln times something with a chain rule, but that is easy because you just take 1 over and then times whatever that chain is. Sounds good? Cool. Of course, I keep the left blank because the left is not y prime if you just take the derivative on both sides. What you did is you took the derivative of this, right? So you better take the derivative of this on the left. At first, this should looks really bad. Okay, I wish this is x, but it's a y. But wait a second, don't we just finish the implicit differentiation? What's this? This is just 1 over y. Pretend it's an x, and when you finish, you just times y prime. Sounds good. What is y prime? That's going to be the whole thing times y on the other side. And by the way, we do know y because y was given. Why was this? The original question. We just put y here. Or, yeah, let's put y here. And then, that's it. Okay? When you do log, the right-hand side becomes super easy. The left-hand side becomes a little bit more complicated, but manageable. So together, we think this is better than what we had before. You go through a small trouble to have a big gain. Sounds good? Okay, so this is what we call a log differentiation. It's not the derivative of the log. Instead, we use the property of the log to make our life easier. Okay, when we say easier, we are pointing specifically to product and the quotient and the power. Okay, so let's write it down. Log differentiation. Okay, here, you need to be very familiar with 3 properties. ln A times B equals ln A plus ln B ln A divided by B. Okay. We knew this before, but the hidden implication here is product rule, quotient rule become summation rule and subtraction rule, which are way easier. That's why we need this. Of course, we have a third property, which later I will show you some example. Okay, that is when you have a power. Certainly this one helps when you have powers, but later we will show this one also help you to do something which are impossible before. For example, like something like x to the x. It's going to be hard, but when you take the log, it becomes x ln x. And for this, you know how to take the derivative by product rule. Okay, but we will save that thing for later. For now, let's just focus on how to make our product and quotient easier. Okay, the detailed procedure are something like this. Y equals some multiplication, some dividing, everywhere. It's going to be a disaster. But then what you do is you apply ln yourself. Okay. Once you do that, the right-hand side, you will be able to simplify to be ln plus ln minus ln minus ln, whatever. But you only have plus or minus. There's no product or quotient. After that, you take the derivative. The derivative on the right-hand side is really just a lot of chain rule. The derivative on the left-hand side will always be this. Still okay? Finally, when you finish, your y prime is just going to be whatever you got here times y. And y, again, you know what y is because y was the original function. You can always just copy it. Then you'll finish the whole thing. Sounds good? Let's try some example. The key is apply a log yourself. The rest is once you finish simplifying, take the derivative. Whatever the answer is, just copy it. Sine cube x tangent x plus e to the x. Three x minus 4 to the 1/2 divided by x minus 2 3/2 times By the way, this is just one option. Of course, you can do it by quotient rule and product rule if you say, I just hate log differentiation. For a problem like this, be my guest. Okay, if you really want to use product rule and quotient rule. Try that yourself. All right. That's a long problem. The first part is try to use log property. Okay, don't take any derivative yet. The second part is take all the derivatives up to the level you feel comfortable. Chain rule. Using the fact. Okay, the rest here is simplification. It's a lot, but really it's worth nothing other than just you're copying everything. You times y on the other side and copy y, right? So I would say the difficult part lies in here and also here. Make sure you check all the work and raise questions if you have. Okay, that's all for today. Tomorrow we will go over more examples. If you have questions, stay here. I will answer them. Okay, otherwise, feel free to leave the room.